In this video, we're going to go through some numerical problems under thermodynamics. Now, this is the first question which is given to us. When 12.17 kilocalories of heat was added to an ideal gas at a constant pressure of 2.46 atm, the volume of the gas increased by 40 cm to the third. Now, we need to find the internal energy, dE, which is stored in the gas. So bringing out the parameters, we have dQ, that is a change in the heat quantity, and that is given as 12.17 kilocalories. Now, if you have a kilo means 1000. So I'm actually going to take that and change this heat quantity to calories. So this is going to be 12.17 multiplied by 1000, and we're going to have this stuff now in calories. So that should give us 12,170 calories. That is the heat quantity. Next up, we have that the pressure is actually constant. So the pressure is equal to 2.46 atm. Next up, we have the volume of the gas. And the volume of the gas here is not actually given as per the first volume and the second volume. Rather, we were actually only given the change in the volume. So V1, we do not know what that is. V2, we do not also know what that is going to be. But we know that dV, which is actually the change, because it is actually represented here, we have it as the increase. So that is going to be 40 cm to the third. Now, because we just need to work the volume of each quantity or substance within this course in terms of liters, we're actually not going to leave the volume of any quantity in cm cube. So we need to change this to liters. Now, how can we do that? First off, you need to know that 10 cm, that is equal to 1 dm. 1 dm is equal to 10 centimeters. Now, what if I took the power of 3 to both sides? That is going to be 10 cm and this to the third. And here we're going to have a 1 dm raised to the third. So distributing the powers, we would have a 10 to the third cm to the third. And here we're going to have a 1 to the third dm to the third. So we know that 1 dm cube is therefore going to be equal to 10 to the third cm cube. Now, 1 dm cube is the same thing as 1 liter. So that is still going to be equal to 10 to the third cm to the third. So this is actually very needful. Now, we know that 1 liter is equal to 10 raised to the power of 3 cm to the third. So we need to change 40 cm to the third in to liters. So this is going to be 40, and you have the x. So we're going to cross multiply, and that will be x multiplied by 10 to the third cm to the third, and this is equal to 1 liter multiplied by 40 cm to the third. So to find the x, we need to take this to the other side, and that will be 1 liter multiplied by 40 cm to the third divided by 10 to the third cm to the third. So that is going to be, we know that this is going to cancel these out, and we would have a 2 left there. So we have 4 multiplied by 10 raised to the power of a negative 2. And we know that cm cube is going to cancel these out. That will leave us with the unit of the liter. So this is what we have. Now, you could well take it further to express it in decimals, and that is going to be 0.04 liters. So in this case, we know that a 40 cm cube is the same thing as 0.04 liters. Now, next up, we need to find what will be the internal energy which is stored in the gas. From the first law, we have that dQ, that is equal to dE plus dW. And dW is equal to pdV. So that will make this to be equal to pdV. Now what is dV? dV in this case is 0.04. So we need to find the internal energy. So I'm going to make that to be the subject, and this is going to be dQ minus pdV. So let us go ahead and find what is going to be. dQ, of course, that is 12,170, and this is minus P. P is 2.46, and we're going to multiply this with the change in the volume, which is actually 0.04. So let us see what that is going to give. This is 12170 minus 2.46 multiplied by 0.04. That gives us 12.169.9. So this is going to be 12.169.9. So in this case, we're going to see that approximately dA is equal to 12.170. Now, what does this actually tell us? How can we analyze this result? Notice that the change in the volume is approximately 0. So this is very close to an isochoric process, an isovolumic process, which actually occurs or takes place at constant volume. So dV for isochoric or isovolumic process, it is actually always equal to 0. dV is equal to 0 for isochoric processes. And for the fact that we have this change approximately 0, that is the reason why we have dE to be exactly equal to what we already have as the dQ. Because under isovolumic processes, dQ will be equal to dE. So approximately we find out this is working. And so that may be an extrapolation that you may want to draw from this answer. But numerically, this is going to be the answer to the question. So that is basically it for this question. Now here is the second question. At a certain pressure P, 14.65 joules of work performed on the gas causes its volume to increase from 2.0 liters to 7.6 liters. And we are required to find the pressure P. So first off, the work. Work is equal to 14.65 joules. And we also have that there is actually an increase from 2.0 liters. So that should be V1. V1 is equal to 2.0 liters. And V2, that is equal to 7.6 liters. Now, for this part of chemistry, we're actually going to deal with the work done always in calories, not in joules. So how can we change this from joules to calories? Now you need to know that 1 calorie is equal to 4.184 joules. So what is going to be 14.65 joules in form of calories? Now of course we need to cross multiply, and X is going to be equal to 1 calorie multiplied, I'm going to use this rather, multiply by 14.65, and that will be divided by 4.184. So 14.65 divided by 4.184. That gives us 3.5. So that is 3.5, and I'm going to write that here. We have 3.5 calories. So that is cal. So we need to find the pressure from here. Now, we know that work done is equal to PdV. And this should be equal to V2 minus V1. So in order to get P will be made the subject. So that is W divided by V2 minus V1. Now what is W? W in this case now is a 3.5, and that will be divided by V2, 7.6 minus 2.0. So let us find out what the answer is. That is 3.5 divided by 7.6 minus 2.0. That gives us 0.625. So this is the answer to the question. The pressure is equal to 0.625 atm. Now here is a third question. Under a process of free expansion, 3.0 moles of a gas undergoes a temperature change of 26 degrees Celsius. Now if CV actually stands for the heat capacity at constant volume. So if CV is equal to 5.0 calories per degree per mole, then we are required to find out what is the change in internal energy, the heat supply, and the enthalpy of the system. So the first parameter that we have is the number of moles, and that is 3.0 moles. And we also have the temperature change. That is going to be dT. dT is equal to 26 degrees Celsius. Now, should we change this to Kelvin, or should we leave it as it is? Now, you need to know that there would actually be no difference, even if we used the degree centigrade or used rather the Kelvin temperature. Now, let us say this were actually expressed in terms of Kelvin. And let's say T1 was given as a 200 degrees Celsius. In Kelvin, that is going to be added to 273. So that should be 473 Kelvin. Now T2 is going to be 226 degrees Celsius. And so in Kelvin temperature, that should be, if we added 3 to this, that will give us a 9. And adding 7 to this, that will give us a 9 also. So that will be 499 Kelvin. Now, if you wanted to find the change in the temperature, of course, this is going to be T2 minus T1, and that is going to be 499 minus 473. And this is still going to give you 26 Kelvin. So in this case, you can see that 26 Kelvin is the same thing as this one. So you don't really need to be bothered about the change in the temperature when it comes to the various units of temperature. So for the change in temperature, the units will not actually make any difference. So we're still going to use a numerical value of 26. That is the equivalent change both in degrees centigrade and in Kelvin. Now next up we have C sub V. That is equal to 5.0 of calories per degree per mole. So we need to find the change in internal energy. Now changing in internal energy, dE, that is equal to NCV dt. And it happens to be that we have all the parameters given here. So that is going to be 3.0 multiplied by C sub V. That is 5.0, and dt is equal to 2.6. Whoa, that is a mistake. That should be 26. So let us see what that is going to give. This is 3.0 multiplied by 5.0 multiplied by 26. So that gives us 390 calories. So that will be the answer for the first part. 390 calories is the answer for the change in internal energy. Next up, we need to find the heat supply. Now, what is the heat supply? That is obviously the value of Q. We need to find the value of Q. Now, you need to know that this process occurred under free expansion. Now, for every free expansion, P is equal to 0, or dP is equal to 0. That is fully the meaning of it. Now, you know that dQ, I'm going to take it as a delta, that is equal to dE or delta E plus delta W. Now, just like we said previously, dW is the same thing as PdV. Now, in this case, P is equal to 0 for free expansion. So that is going to make this stuff to become a 0. And therefore, dQ will be exactly equal to dE. So in this case, we know that under free expansion, dE will completely be equal to the heat content. Remember, that is at constant pressure. So that is the same thing as 390 calories. So that is the answer for this one. Now the last one there is for us to find the enthalpy of the system. Now, enthalpy, H, that is equal to E plus PV. If you wanted to find the change in this is going to be dH and this will be dE plus delta PV. Now we already know that P is equal to 0 for free expansion. So H is exactly equal to E, or dH is equal to dE. So in this case, we also have that dH that is equal to dE. And so that will be equal to 390 calories. So those are the answers for this question. Now the fourth question says, an ideal gas underwent an isochoric process when 278 calories of heat were supplied to it. So we are required to find out the work done, the volume, as well as a change in internal energy. So let us write up Q. Q is equal to 278 calories. And we know that for isochoric processes, dV is going to be equal to 0. And therefore, V is going to be equal to 0. So we need to find out what W is going to be. Now, this is dQ, or I might rather take it back to this. This is E plus a W, right? So we know that dQ is therefore going to be dE plus dW. But dW is the same thing as PdV. So this is dE plus PdV. And since we have that dV is always going to be equal to 0 for isochoric process, this is actually going to change and leave. Therefore, we're going to have dQ to be equal to dE. So in this case, we already know what dE is. dE, that is going to be equal to dQ. And so that is also equal to 278 calories. And this is the answer for the first part. Next up, we need to find out what the work done is. Now, we know that work done is equal to PdV. Unfortunately, dV is equal to 0. So work done is obviously going to be equal to 0. That will be the answer for the work. So we have dE. We also have dW, or the W. And V also is equal to 0. So these are the basic things you need. These are the answers to the question. Now the fifth question says, the internal energy of 5.0 moles of an ideal gas is giving us 147 joules. If the initial and final final temperatures for the gas are 25 degrees Celsius and 47 degrees Celsius respectively, then we should find what CV is and what C sub P is. So the internal energy, dE, that is equal to, so I need to write it this way. This is 1.47 joules. Now, as usual, we need to change this from this form into calories. So we know 1 calorie is equal to 4.184 joules. So in order to change this stuff into calories, we need to take this and divide it into this stuff. So that is going to be 147 divided by 4.187. So that will be 35.11. That is 35.11 calorie. Now we have the number of moles to be equal to 5.0 moles. And we have the initial temperature, T1, that is equal to 25 degrees Celsius. Now, we need to change this. Do we actually need to change it? Because we are also going to need, well, I'm going to just go up gradually for now. But in the end, you're actually going to find that we would not actually need to have changed this. But let us just do that for now. If we added 273 to this, so that is 273 plus 25. That will give us 298. So that is 298 Kelvin. And T2 is equal to 47 degrees Celsius. So this is going to be 273 plus 47. And let us see what that is going to give. If we have this plus this, that is 10. And we have 1, so this is 7 plus 5. So that is a 12. So that will be 2. And then you carry a 1 here. So that is 320. Now, we need to find dt therefore. So dt will be equal to T1. Well, that should be T2. T2 minus T1. Now, T2 is 320 Kelvin. And T1 is 298. So this is 320 minus 298. And that gives us 22. So that will be 22 Kelvin temperature. But if you actually took this and worked the difference, you would still find that 47 minus 25, that is still equal to 25 degrees Celsius. So this actually proves the point. If you are required to find out the change or the difference in temperature, you don't actually need to change or convert the units of the temperature to any other form. You could well go ahead and that will pretty much be the same thing. As far as we're talking about degree Celsius and degree Kelvin, or Kelvin temperature rather. So we are required to find CV. Now we know that dA is equal to NC sub V dt. So we need to find C sub V. In order to do that, we're going to have dE, and that will be divided by N dt. So I'm going to wipe these out. And here we're going to have a C sub V. dE is 35.11, and this is divided by N, which is 5. And that will be multiplied by dt. So dt is 22. So C sub V is equal to 35.11, 35.11 divided by 5 multiplied by 22. So that gives us 0.31918. So what I'm going to do, I will just approximate it. That is 0.32. So this will be calories per degree per mole. So that is C sub V. Next up, we need to find what will be CP. How can we find CP? Now we know that C sub P minus C sub V is equal to R. We have actually made a video that completely explains this derivation. And if you have not actually gone through that video, I would actually recommend that you go through it. The link to the video has actually been attached in the description section below. So R, in this case, we're going to use R as 1.987. That is if we wanted to find our answers in terms of calories per degree per mole. Because this is what it is here. This is cal per degree per mole. So let us look at that. This is CP, and that will be equal to R plus C sub V. So I'm going to wipe these out also. So C sub P is equal to R. R is 1.987. And that will be added to 0.32. So let's see what that is going to give. That is 1.987 plus 0.32. So that gives us a 2.307. So this is a 2.307. And of course, this is in calorie per degree per mole. So that is the answer for the heat capacity at constant pressure. Now we need to find the last thing, which is the change in the heat. Now change in the heat is also N multiplied by C sub P dt. Now we know what N is. N is actually 5 moles. And we also know what Cp is. That is 2.307. And we also know what dt is. dt is actually 22. So let us find out what that is going to give. That is 5 multiplied by 2.307. That is multiplied by 22. So that will give us 253.77. Now, this of course is going to be in calories. So that is dq. dq is equal to 253.77. That is the answer for that question. Now here is the sixth question. Calculate the maximum work obtainable by the isothermal reversible expansion of 2 moles of nitrogen gas from 10 liters to 20 liters at 25 degrees Celsius. So we have the number of moles N. N is equal to 2.0 moles. And we also have the change in the volume. So V1 is 10 liters. And V2, that is equal to 20. So that is 20 liters. And we have the temperature. Temperature is 25 degrees Celsius. But we cannot leave this in its form, since this is the only temperature which was given to us. So this is actually going to be a constant temperature, and hence we have it to be an isothermal process. So we would need to change this to Kelvin temperature. So that is going to be a 25 plus 273. So this is going to give us a 298 in Kelvin. Now, the work done under an isothermal process is 2.303 multiplied by N multiplied by R multiplied by T multiplied by log to the base 10 of a V2 divided by V1. Now, this is going to give us 2.303 multiplied by N. Now, N in this case is 2. And R, what are we going to use for R? Should we use 0.0821 or should we use 1.987? Or are we going to use 8.314? Now the formula that we're actually going to use basically depends on the type of the unit for the work that we are actually looking for. If we used this form, then we would actually have the work done in another form. If we used this 1.987, then we're actually looking for the work done in calories. If we used 8.314, we're actually looking for the work done in joules. Now we don't need this. We need to find the work done always in calories. If we use this one, that would actually be a kilo. But if we use this, that is a normal calories. So we're going to go with this one and take this one out. So that is multiplied by 1.987. And this will be multiplied by the temperature. And the temperature in this case is actually 298. And that is multiplied by log to the base 10 of V2. So V2 is 20. And V1, that is 10. So let us see what that is going to give. we have 2.303 multiplied by 2 multiplied by 1.987, and that will be multiplied by 298. That is multiplied by log 20 divided by 10. So that gives us 821 joules. Well, that is not joules. That will be calories in this case. So that is going to be the answer for the work done. 821 calories. Now this is the 7th question. An ideal gas undergoes a reversible isothermal expansion from an initial volume V1 to a final volume 10 V1, and thereby does 10,000 calories of work. So we are required to find out what is the first volume and to find out what is going to be the temperature. But the initial pressure here is 100 atm. So let us bring out the parameters once more. We have a V1. Now V1 was not told us, so we're just going to leave that as a V1. And V2 is 10 V1. And we also have the work. So W is equal to 10,000 calories of work. Okay. And we also have the initial pressure. So that is P1. P1 is equal to 100 atm. So we are required to find what is going to be V1. How can we find V1? Now we know that this is an isothermal process. So for an isothermal process, we must have that W is equal to 2.303 nRT multiplied by log of V2 divided by V1. That is what we should have. Now, it happens to be that we do not really know what V1 is, but we can find something from here. So let us try to do that. First off, we're gonna we know that the work done is 10,000 calories of work, so we need to find the temperature from here. So let us try to do that. W is equal to 2.303 nRT multiplied by log to the base 10 of V2. V2 is 10 V1 and divided by V1, right? So we know this is going to cancel out, and we're going to have W is equal to 2.303 nRT log to the 10 to the base 10 of 10. This stuff is going to change to a 1. So we would have W is equal to 2.303 nRT. So we're going to have, we're going to find the temperature here first of all. So T, that is going to be W divided by 2.3. So I need to write that out. 303 nR. Now work done, we have that to be 10,000 calories. And we have 2.303. This is multiplied by N. Now N in this case, that was the number of moles. We were given 2 moles. And R, because we have the unit of the work to be in calories, this is actually going to be a 1.987 because we want to find the answer in degree Celsius. So T is going to be 10,000 and that divided by 2.303 multiplied by 2 multiplied by 1.987. So that gives us 1092.64. 1092.64. This is going to be in Kelvin. Now next up, we need to find what V1 is. Now we could use the formula of the ideal gas equation in order to find out what is going to be V1. We know that PV is equal to nRT. Now under isothermal conditions, we're not going to change the T. But P1 V1 is going to be equal to nRT, as well as P2 V2. That will be nRT. And if you go on, you're going to have that Pn Vn is equal to nRT, where n stands for any natural number. Because in this case, we're keeping T to be constant. So we actually don't need this equation. We're going to make use of this one. So here we're going to have V1, and V1 is going to be nRT. That will be divided by P1. So here we can use it to find what V1 is. So this is n, and we're going to multiply with R. Now here we need R, and R needs to be found in liters. So in order to get the answer in liters, we're going to use a 0.0821 or 0.082. And T is 1092.64. So this is now divided by P1. And P1 is initial pressure. That was given to be 100. So we can well tell what the answer will be from here. So V1 therefore is going to be N. Well, we were given what N is, so I need to write that there. This is going to be a 2. So this is 2 multiplied by 0.0821, and that is multiplied by 1092.64. And that is divided by 100. So this gives us 1.794. 1.794 liters. That is the answer to V1. So we already had what T is. We found that is the temperature. That was 1092.64. So those are the answers to this question. Now here is the 8th question. Calculate Q, which is the heat, and W, which is the work done, and dE, which is the change in internal energy, for the reversible expansion of 10 moles of an ideal gas from an initial pressure of 1 atm to a final pressure of 0.1 atm at a constant temperature of 0 degrees Celsius. So we have T, which is a constant temperature. That is 0 degrees Celsius. Now we need to change this because the temperature is constant. So this would need to be changed. Now we're going to add the absolute temperature, which is a 273.15. We're going to add it to 0. And of course, that is going to give us the same thing. So 273.15 Kelvin. Now we also have P1. P1 is 1 atm. And we have P2. P2 is 0.1 atm. Now we also have the number of moles here. That is 10 moles. And that is basically it. So we need to find what is Q, what is W and dE. First off, you need to know that this is a process which is taking place at constant temperature. Now at constant temperature, dT is equal to 0. And hence we're going to say we have an isothermal process right here. So for isothermal processes, dE obviously is going to be equal to 0. Why is that? We have dE to be equal to N CV dt. Now dt is already equal to 0. So that is going to make dE to be equal to 0 because we have dt to be equal to 0. So this is the first answer. dE is equal to 0. Next up, we need to find what Q and W is. How can you find it? So we need to find the work done under the isothermal conditions. So that will obviously be 2.303 nRT multiplied by logarithm to the base 10 of, we should have had V2 divided by V1. But in this case, we do not really know what the first volume is. Neither do we know what V2 is. So we're actually going to use the Boyle's law and take that to pressures. So instead of V2 divided by V1, we're going to have P1 divided by P2. So this is going to be 2.303. So I'm going to take these up. W is equal to 2.303 multiplied by N. So N is up 10. And we have R. So what is going to be R in this case? Because we need the work done to be in calories, we're going to use 1.987. And we need to multiply that with temperature. Temperature is 273.15. And we need to multiply that with logarithm. That is log to the base 10 of P1. Now P1 is 1 and P2 is 0.1. So we can tell what W is from here. So that is going to be 2.303 multiplied by 10 multiplied by 1.987. That will be multiplied by 273.15. That is multiplied again by log to the base 10 of 1 divided by 0.1. So the work done here is 12,499.5. And this, of course, is in colors. So that will be the work done in this case. Now, because we have from the first law equation that Q is equal to U, or in this case E, plus W, we know that A is equal to 0. So we have Q to be equal to W, and that obviously will be equal to 12,499.5 calories. So that is going to be the heat quantity for that process. That is the answer to the question. Now here is the 9th question. So we just got one more question and then we'll be done with this video. So we are asked that 2 moles of nitrogen gas at STP are compressed reversibly to a volume of 10 liters. Now we are required to calculate the work done when the process is carried out isothermally as well as adiabatically. Now we're given the gamma ratio that is equal to 1.40. So first off, we have that the number of moles is equal to 2. And we have this process occurring at standard temperature and pressure. Now if you have that, that means the first temperature, T1, that is going to be 273.15 Kelvin. Now P1, initial pressure, that is going to be 1 atm. And we also have that the stuff was compressed reversibly to a volume of 10 liters. So in that case, we're going to say V2 is equal to 10 liters. Because we have that stuff was compressed reversibly to a volume. So that moved from one volume to another one. And that is going to be V2 then. Now, if we want to calculate the work done, we know that work done is equal to 2.303. So I'm having some big challenge writing this out. That is 2.303 log to the base 10 of V2 divided by V1. Now it happens to be that we have not yet found what V1 is. How can you find V1? What is going to be the answer for V1? So this would actually be a little bit trickish, except you know that at STP, 1 mole of a gas is actually equal to 22.4 dm cube. Now dm cube is the same thing as liters, so this is 22.4 liters. But that is for 1 mole of a gas, an ideal gas. Now in this case, we have 2 moles of the gas. We were given 2 moles for the gas. So we're going to have V1 to be equal to 2 multiplied by 22.4 liters. So obviously that should give us 44.8 liters, right? So we have everything. So we can actually find out what is going to be the work done from here. So W is going to be equal to 2.303 multiplied by N. Now N in this case is a 2.